Before I start, I want to thank Indira, Louis, and Karen for organizing this conference. So today I want to talk about Coxeter groups and Kazhdan's property T. So in particular, I want to share with you some results regarding the conjecture that automorphism groups of Coxeter groups do not have property T. So as the main objects in my talk are Coxeter groups, I start with the definition of this object. So given a finite simplicial graph gamma with an H labeling, the Coxeter group W gamma associated to gamma is a group with the following presentation. So the generator set is equal to the vertex set. For each vertex V, we have a relation V square. And for each edge in the graph, we have a relation VW to the power of the H label. So let us spend some time at examples. So this graph has two vertices and one edge. So the corresponding Coxeter group has two generators and three relations. And one can show that the algebraic structure of this group is as follows. So the Coxeter group is a direct product of two copies of the twos. And we can also describe this group as an isometry group of a geometric object, so of a two-colored square. So we only allow reflections. So one more example. Again, we have a graph with the vertices and one edge. So the corresponding Coxeter group has again two generators and three relations. So the algebraic structure of this group is as follows. So one can show that this group is a semi-direct product of Z5 with the 2. And this group can also be described as the isometry group of a geometric object of the pentagon. Okay, so one more example. So this graph has no edges, hence the corresponding Coxeter group is equal to the free product of the twos. In this graph, no edge is missing, and all H labels are equal to 2. Hence, the corresponding Coxeter group is a direct product of the twos. So if all H labels of the graph are equal to, then the Coxeter group is called right-angled, because we can construct a cube complex on that the group acts nicely. So usually one says that right-angled Coxeter groups interpolate between free product of the twos and direct product of the twos. Okay, one more example. So the corresponding Coxeter group of this graph has the following structure. So for experts, this Coxeter group is the affine Coxeter group of type A3 tilde and can be geometrically described as the isometry group of a very nice styling of R3. So let's talk about properties of Coxeter groups. So Coxeter groups were named after Harold Scott MacDonald Coxeter. So it is obvious that Coxeter groups are finitely presented. Finite Coxeter groups were classified in terms of Dinkin diagrams by Coxeter. The Coxeter groups are linear groups. Coxeter groups are Cat0 groups. And a Coxeter group W gamma is chromorph-hyperbolic if and only if the Poisson non-hyperbolic group Z times Z is not a subgroup of W gamma. Okay, next fact. A Coxeter group is meanable if and only if the free group of two generators is not a subgroup of W gamma. Okay, and the next fact. So a Coxeter group is either virtually free abelian or large. So today, our focus is on the fixed point properties, so in particular on Serre's property of A and Kazhdan's property T. So let us first recall the definition of property of A. Okay, so let A be the class of simply short trees. A group G is said to have Serre's property of A if any simplicial action of G without inversion on any member of A has a fixed point. So it follows from Serre's results that a Coxeter group W gamma has Serre's property of A if and only if gamma is a complete graph. So no edge in the defining graph is missing. Next definition. So let H be the class of real Hilbert spaces. A countable group G is said to have Kazhdan's property T if any action of G by isometries on any member of H has a fixed point. So property T was introduced by Kazhdan for topological groups in terms of unitary representations. So we are not going to recall the original definition. The definition of property T in terms of fixed points was given by Delorme and Guillaume. So the last fact about Coxeter groups is as follows. The Coxeter group W gamma has Kazhdan's property T if and only if the corresponding Coxeter group, so W gamma, is finite. So the proof by Batsaiko, Januszkiewicz, and Spazia has a geometric flavor. So they used the action of a Coxeter group on the corresponding Coxeter complex. So they constructed a really nice embedding of the Coxeter complex in a Hilbert space in such a way that the Coxeter group acts by isometries with respect to the induced metric. So many properties of a Coxeter group can be checked easily on the graph gamma. So let us figure out some properties of the right-angled Coxeter group W gamma where the graph is a Peterson graph. Okay, so assume that all H labels are 2, then the corresponding right-angled Coxeter group is infinite. So that's easy. So this follows from the fact that a right-angled Coxeter group is finite if and only if the defining graph is complete. Okay, the group is hyperbolic. So it was proven by Mousson that a right-angled Coxeter group is hyperbolic if and only if gamma has no squares as full subgraphs. And it is obvious that the Peterson graph has no squares. Okay, the Coxeter group is not virtually free. So virtually free Coxeter groups were described by Michalik and Chanst. So they showed that a right-angled Coxeter group is virtually free if and only if it has no cycles of lengths greater or equal 4. So the Peterson graph has a pentagon as a subgraph here. Hence, the corresponding Coxeter group is not virtually free. Okay, it has no T because the group is infinite. And the Peterson graph is not complete. Hence no FA. But the automorphism group of W gamma has FA. So this result was recently proven by Niels Leder in his PhD thesis. Okay, so our focus today is on the fixed point property T. So let us proceed with 10 facts about T. So property T was introduced by Kazhdan for locally compact groups in terms of unitary representations. So what can property T tell us about the group? So Kazhdan proved that if a locally compact group has T, then it is compactly generated. And if a group has T, then all its lattices satisfies T. Hence, all lattices of a T group are finitely generated. Okay, so Kazhdan's motivation was to use this property to prove that a large class of lattices in Lie groups are finitely generated. Okay, so the Lie group SLNR has T, hence all lattices in SLNR are finitely generated. So for example, it is not hard to prove that all lattices in the group consisting of real numbers are finitely generated, but it is not so easy to show that all lattices in nice Lie groups are finitely generated. Okay, so SLN-Z is the lattice in SLNR, hence has T. Okay, so Kazhdan's property T is inherited by quotients and is preserved under taking finite index subgroups. If a group G acts fixed point freely on a tree, then G does not satisfy property T. So this connection between property T and Serre's property of A was proven independently by Alperin and Vatatani. So trees are one-dimensional K0 cube complexes. And Niblo and Reeves generalize this fact to higher dimensional cube complexes. So they proved if a group G acts fixed point freely on a K0 cube complex, then G does not satisfy property T. And this fact was recently used by Osaida to show that Bernstein groups do not have T. So we are mostly interested in discrete groups with property T, and we have the following motivation to search for a discrete T group. So if a nice discrete group G has T, then one can construct a family of really nice graphs, so a family of expanders, using Kelly graphs of finite quotients. So I like groups and graphs and other geometric objects, and I like to construct nice geometric objects using groups. And this fact is enough motivation for me to search for T groups. So free groups and free abelian groups do not have property T, but the automorphous group of a free group has T, and the automorphous group of a free abelian group has T. So Coxeter groups are well understood object in geometric group theory. So they provide interesting examples and counterexamples to many conjectures. And I think it is natural to ask if the automorphous group of a nice Coxeter group has T. So we conjecture that this is not the case. So the automorphism group of an infinite Coxeter group does not have Kazhdan's property T. So some results in this direction. So let W gamma be an infinite Coxeter group. So if gamma is discrete, so if gamma has no edges, then out W gamma does not have property T. And this result holds for all right-angled Coxeter groups. So if W gamma is a right-angled one, then the automorphous group does not have property T. Okay, let's talk about methods to prove that a group does not have T. So if the outer automorphous group is finite, then the automorphous group of the Coxeter group does not have T. So why? So this follows from the fact that the center of a Coxeter group is always finite, and the quotient W gamma, center of W gamma, does not have T. So it was proven by Howlett, Rolle, and Taylor that if gamma is complete, then the outer automorphous group of the Coxeter group is finite. Hence, the automorphous group has no T. Okay. So Niblo and Reeves constructed for each Coxeter group a K0 cube complex on which the group acts fixed point freely. So what can we do with this complex? So we can try to extend the action of the Coxeter group W gamma on the corresponding Niblo-Rilska zero-cube complex to an action of a finite index subgroup of out W gamma. So, so for some Coxeter groups, this is doable. But for a general Coxeter group, we don't even know if the automorphism group is finitely generated or not. Okay, so we can try to show that the automorphism group maps virtually onto W gamma or onto a special infinite subgroup of W gamma. And this is what we are going to do. So let me state the main theorem. So let W gamma be an infinite Coxeter group. If gamma has a maximal complete subgraph delta such that the center of W delta is trivial, so this assumption can be checked easily on the graph gamma. So then the automorphism group virtually surjects onto W gamma. And in that case, the automorphism group does not have T. Okay, the second result is as follows. So let W gamma be an infinite Coxeter group. If there exist two non-adjacent even vertices, VW in gamma, then the automorphism group virtually surjects onto a free product of the twos. So in particular, no T for the automorphism group. And what do I mean by an even vertex? So a vertex V in V is called even if all H labels of E in E with V in E are even. So let us discuss some examples. Okay, so the corresponding Coxeter group of this graph is a right-angled one, and it is infinite. So hence, the group has no T. So what about this graph? Okay, so this graph has two non-adjacent even vertices. So this vertex is an even one, and this vertex is an even one. Hence, the group out W gamma has no T by part 2 of the main theorem. Okay, next result. Or next example. So this graph has only one even vertex, this one. So we cannot apply part 2 of the main theorem, but this graph has a maximal complete subgraph delta such that W delta is an irreducible infinite Coxeter group. So let us consider this triangle. So triangle is a maximal complete subgraph in the graph gamma. The corresponding special Coxeter subgroup is an affine one of type A2 tilde. It is irreducible, and irreducible Coxeter groups have always trivial center. Hence, the automorphism group has no T by part 1 of the main theorem. Okay, some more results. So let W gamma be an infinite Coxeter group again. So if gamma has no cycle of length 3, then the automorphism group has no T. So why? So in this case, maximal complete subgraphs in gamma are edges. And if gamma has an edge where the edge label is odd, then the center of this corresponding special subgroup is trivial. And we can apply part 1 of the main theorem to see that the automorphism group has no T. So otherwise, all H labels are even. And by part 2 of the main theorem follows that the automorphism group has no T. Okay, So if all H labels are even, then the automorphism group does not have property T. So why? So if gamma is complete, then the outer automorphism group is finite. Hence, the automorphism group has no T. And if gamma is not complete, then gamma has two non-adjacent even vertices. Hence, by part 2 of the main theorem, the automorphism group does not satisfy property T. So if all H labels are at least 3, then out W gamma does not have property T. So it follows from a characterization of finite Coxeter groups that if gamma has at least 3 vertices and all H labels are at least 3, then all special subgroups of W gamma are infinite and irreducible. So all non-trivial special subgroups. So all infinite special subgroups of W gamma are irreducible. So irreducible infinite Coxeter groups have always trivial center. So in particular, gamma has a maximal complete subgraph such that the corresponding special subgroup has trivial center. Hence, by part 1 of the main theorem, the automorphism group has no T. Okay, so one more example. So what about this graph? Okay, so this graph has 2 connected components and has no even vertices. So maximal complete subgraphs are triangles. So we have 8 triangles. And the corresponding special subgroup of a triangle has non-trivial center. So we cannot apply the results in the main theorem to this automorphism group. So question, does out W gamma satisfy property T? We don't know. Okay, so back to the main theorem. And today I want to discuss the main steps in the proof of part 1. Okay, so an important puzzle piece of the proof is the following lemma. So let gamma be a Coxeter graph and delta 1 to delta n the maximal complete subgraphs. We define W delta I in brackets as the following set. Then the following map is a well-defined homomorphism. And in particular, the kernel of phi has finite index in the automorphism group. Okay. Okay, so the idea of the proof is based on the following fact. Maximal FA subgroups of a Coxeter group W gamma are exactly conjugates of special subgroups W delta I. And this result was proven by Michalik and Chanst. Okay, so for W delta I, the group, so the image of W delta I under F is again a maximal FA subgroup. So we know that the existent J such that we have this relation. So such that the image of W delta I under F is in this set. Okay, and then one can prove that the image of F is indeed a bijection and phi is a homomorphism. Okay, one remark. So for F in the kernel of phi, the existent A in W gamma such that the image of W delta I under F is a conjugate of W delta I by A. And we can compose the map F with CA inverse, where CA inverse is a conjugation by A inverse, and then CA inverse composed with F is an automorphism of W delta I. Okay, so back to the theorem, and let us discuss the main steps in the proof. Okay, first we construct a map psi from kernel of phi to the outer automorphism group of W delta. And then we show that the kernel of psi maps onto W gamma. So the kernel of psi has finite index in the automorphism group of W gamma, and W gamma does not satisfy property T, since the group out W gamma does not have property T neither. Okay, so let us discuss the main step in the proof more precisely. So we already know that for F in the kernel of psi, there exists an A in W gamma such that the image of W delta under F is a conjugate of W delta by A. So, and then we set the image of F under psi equal CA inverse composed with F, and we take the conjugacy class, where CA inverse is again conjugation by A inverse. And this map is a well-defined homomorphism. One have to check it. So then we construct a map psi from kernel of psi to W gamma. So for F in the kernel of psi, there exists an B in W gamma such that the image of W under F is a conjugation by B for all W in W delta. And we set psi F equal B. Okay, so this map is a well-defined one. So why? Because this element B is unique with this property. Okay, so assume that there exists a C in W gamma such that the image of W under F is a conjugation by C. But then B inverse C is in the centralizer of W delta in W gamma. And this centralizer is equal to the center of W delta, and the center of W delta is by assumption trivial. So B is equal C, and one can also prove that the map psi is an epimorphism. Okay. Okay, so recall a group G is called large if it virtually surjects onto the free group of two generators. So it is known that any Coxeter group is either virtually abelian or large. So moreover, these properties can be verified easily on the Coxeter graph. So concerning largeness of automorphism groups of Coxeter groups, so it was proven by Saale and Suse that the outer automorphism group of a right-angled Coxeter group is either large or virtually abelian. So we obtain the following result concerning largeness of automorphism groups. So let W gamma be a large Coxeter group. If gamma has a maximum complete subgraph delta, such that the center of W delta is trivial, then the group out W gamma is large. Really nice result. So what's next? A very interesting class of groups is a class consisting of right-angled arting groups. So let us give a quick definition. So given a finite simple Schur graph gamma, the right-angled arting group A gamma is defined as follows. So the generator set is equal to the vertex set and of the graph, and for each edge in the graph we have one relation. So for each edge uv we have a relation uv u minus 1 v to the power of minus 1. Okay, so let us proceed with some examples regarding property T of automorphism group of a right-angled arting group. So the group out F5 has T. For n bigger or equals 6, the group out Fn has T, but the group out AC5, where C5 is the pentagon, does not have T. And there are more examples in the literature. I plan to answer the following question. So for which shape of the graph gamma does the automorphism group out A gamma have Kazhdan's property T? So I have results for small graphs, but these results will be the topic for my next talk. So thank you for your attention.